we actually start on time? Is that allowed? Sorry. Okay. All right, we're going to get into some new content today, looking at search trees. Specifically, we're going to stick to binary search trees because they're a lot easier than the other kind of interesting search trees. All sorts of smart people have done really cool things with other forms of search trees. That's more of an advanced topic. So we're going to stick to the easy one. So if you think back to binary trees, right, that is a tree structure that has at most two children, the left child and the right child. And we looked at a couple different ways of storing that data. And you can do it with links, or you can do it with an array-based structure or a list-based structure here. And either work, it sort of depends on what you expect your tree to look like. So this will be week 12. Oh, and I forgot to open up chat on the other screen here. I heard a noise though. Hector, my friend, thank you so much for donating those bits to the Student Scholarship Fund at the University of Michigan Dearborn College of Engineering and Computer Science. You, sir, are a legend. I gotta add you somewhere, like on a Legends page, right? That'd be cool. So, looking at trees and search trees, if we know that our tree will generally be balanced and have mostly the same number of children on the left and on the right, and mostly be full-ish, doesn't have to be exactly full, but mostly a full form, the array-based storage is more efficient, right? And it's quick and easy to do the math to traverse. We don't need direct links. We can just do the math on what is my index, what is my parent's index, and we can do some of that arithmetic real quick. But you get some really interesting forms of trees here. And I think we looked at one that was basically a list. So if I add, say, a 7 and a 10 and a 3 and a 2 and a 9, this is a binary tree, right? This is a node. It just has no left child, right? All of these only have right children. I really should have brought my drawing pad. I keep forgetting to put that in my backpack. Right? This is a binary tree. It's a really bad form and structure of a binary tree, and storing this in an array is terribly inefficient because we have, what, level 0, 1, 2, 3, 4, so 2 to the 4th, something like that number of positions, or 2 to the 5th minus 1 number of positions in my array. I forget the arithmetic off the top of my head. But there's a lot of empty space here. So some of use on mobile, I can scan a QR code. Well, that's kind of fun. All right, anyway, sorry. I hadn't seen that before. So I think if we are simply doing the basic binary search tree form, it's easy enough for us to use links. The more advanced, more interesting binary search trees you'll learn all about with techniques to keep them balanced are a little harder, and those would fit better in the array-based form because there's a process that keeps them from getting in this sort of structure. And you can read all about it in the text. You'll get to it if you take the data structures and algorithms analysis class. There's a couple common techniques. There are AVL trees and red-black trees, and really smart people have done these things. They're not super confusing, but it's a lot more that goes on. So when you go add a value, you have to make sure you find the right location. I guess I should say what a binary search tree is at first. I skipped right over that. I'm sorry. I've had a lot of coffee already today, and I've moved on to Coke now because I ran out of coffee. All right. So a binary search tree is a binary tree with a simple rule. So if you are less than a value, you're on the left. If you are more than a value, you're on the right. Some value. That's it. That's the entire rule. So if we were to throw out a couple numbers here, we can start building the binary tree based on the order in which things are added. So what this gives you is a sorted order, because things that are less than will be on the left, things that are greater than will be on the right. So when you traverse the tree, we briefly looked at a couple of traversals. There's the in-order traversal, the pre-order traversal, the post-order traversal. I know it was a while ago and we moved on to other topics, and now we're coming back to it. It's a little weird, they're out of order. But if you traverse it in order, remember the in-order traversal said, let's go as far left as possible. We'll do the thing on the left, and then we'll do the node in the center, and then we'll do the node on the right. And it had this recursive form. So if we had other nodes in here, right, like 12, and this one had something on the right, I don't know, 2, something, right? We said left center right. So there is no left here, nothing to do. So center would be 7. And we go to the right. Once you get to the right, you repeat the process. Remember, it's recursive. So as soon as we get here, we go to the left. So left, no left of here. So we get a 1. Center, we get the 1. Right, we go over here, we get the 2. And on and on and on. So this particular left, center, right, the in-order traversal, if we're in a binary search tree form, will give you the sorted order. Remember, we talked about trees a while back. The insertion time on a tree is generally proportional to the height. This idea, it should grow logarithmically with the number of n values, because you assume you've got some sort of good balance here, and you're going to have less height than you have values. Now, again, you can get this chain where your height is the number of values you have. We're going to assume we're going to do a smart thing later and never run into this. So it could, in worst case, perform badly. But in general, on average, right, we're going to do the right thing and keep our tree in a somewhat balanced form. We should get logarithmic performance for inserts, because we just have to navigate which left, center, right we need to go for these values here. That's it. So you say, if it's less than, go to the left. If it's greater than, go to the right. That's all you do. So throw out a couple numbers, and we'll start adding them in this tree form and see if we can build a tree. Now, the other thing you get here is this is a set. It does not do well with duplicate values, because a duplicate value is not less than and it's not greater than. You can't go left and you can't go right. So it just doesn't work. So these are sets here when you deal with binary search trees typically. So just shout a couple numbers out at me, and we'll add them to the tree following this form and see what we get. 15. All right, so 15 becomes the root because we had no root. And let's try not to go in order. Let's try to do some lower, some greater, because otherwise we'll get a chain if we just go up. 12. Okay, so 12 is less than, so we're going to go to the left. We have no left, so we'll add it in. 7. Okay, so it's less than 15, we go left. It's less than 12, we go left. It has no left, now we get a 7. 23. Right, 23 is greater than 15, we go right. There is no right, now we have a 23. 14. Right, 14 is less than 15, we go left. 14 is greater than 12, we go right. There is no right child, now we have 14. 18. 18 is more than 15, we go right. 18 is less than 23, we go left. 18. 5. 5 is less than 15, 5 is less than 12, 5 is less than 7, we go left, we have a 5, and on and on and on. So this is just a recursive process. It says, hey, if you're less than, if there's not a left child, now you're a left child. If there is a left child, recurse at that left child. The same sort of recursive form that we've done before, where it just works its way down the tree. So we did this with the heaping process, where we would upheap or downheap, and we just kept on going. Similar idea, we just keep on going, right? If there's a child, okay, we can't go there. Let's just keep going from the left child. Those sorts of values. So I think we'll actually use the array-based form, because I think we had more of that implemented. Does that ring? I think we did more, or do we implement them both? I think I did the linked-based one, and the array-based one we did in lab. Then we came back and finished. Does that ring a bell? Let me go grab that. So let me come in here and grab our code. So we want our our trees here. And we had, it was just in the lab, wasn't it? This was, goodness. It was in priority queues, right? Did we finish out the tree? Is that what it was? Oh, I can't even remember. Can't remember where we got it from. Might have been in the lab. So lab, yeah, okay. Here's the linked binary tree. Okay, did we never finish the array-based binary tree or the list-based binary tree? Now I'm really confused. Binary tree, we did it, right? Really? Did I spell it wrong? Tree. Let's see what we get for tree. Huh. Oh, we just asked ChatGPT for it. That's what we did. That's right, because the arithmetic was going to be hard for us. And then we modified it. Okay. So we'll just take our linked base tree. I think is probably the easiest then. Because we heavily modified that one. We should be able to use this position, root, parent, left, right, sibling, child, add root, add left, add right. Okay. we'll take all of this here, and we'll start tree, essentially here, and we'll go modify this to be a binary search tree. So we can say, hey, this came from, be good about citing our sources here, right? Now, you do notice, I don't know if you noticed, you should notice, this URL has this big, long, ugly thing here. It's like GUID, I think, or it might be a hash. This was probably a hash. It looks too long for GUID. This hash then will always be the exact same here. It's this commit hash, essentially here. Versus if you just look at the code, say, I don't know, where's someone else we have in here, 7 trees, main. You can look at a particular version here from the main branch. So if you link and it has a branch name here, for now, what we've always done working on main, you'll get the current latest version. So it's possible you cite it and say, hey, here's my source, main, and then it changes out from under you. So that the hash-based links are better. Essentially, you can like view the file at that given hash or something. If you've got the hash in there, it will always be there, unless someone does a really bad thing in Git and blows away history, which is really frowned upon. That's a big no-no. But I don't know if you've seen, sometimes the URLs look different. For our purposes, it doesn't matter much. It's not gonna make any big difference. But you'll notice it doesn't say main is all. All right. So we have a binary search tree. So with the binary search tree, we can still be positional. That's fine. But you don't add left and add right. You don't add root. All you do is add. So I'm going to go and make these private here because we're going to use the add left and add right here in a minute. I'm going to go refactor, rename these here to indicate these should be private values. That was the wrong key. There we go. The refactor, rename. Because with the binary search tree, all you're going to do is add a value, and we'll figure out where it goes. Right? You don't tell me if it's the left or the right child. Rename that one. And right. Okay. Replace. We're not going to replace either because this is not going to do that because you can't put a new value in an old place. And that's no good. So we'll get rid of that one. Delete should be okay, but I think this. We need to make sure that we don't put the small. Oh no, it should be okay. Either one, right? And if we have 2 children, it's okay. We can figure out which child we need to use. This gets tricky here, so we'll come back to this. It's tricky to figure out which child to put in here. There's a rule that we're going to use that makes this a little easier, but you can't just take the left child or the right child and put it in here because that child might also have a left child or right child already, right? So it's kind of a not ideal situation there. So we'll come back to that one. Depth is fine, height is fine, height is fine. Get the children of a position, sure. Get the sibling of a position, sure, why not? Get the left, get the right, if it's empty, okay. Number of children, parent root, cool. So we don't have an iterator, but that'll be okay. We can say, like, give me every item in here. I think we wrote that one for the list-based one. I don't remember if we got that one out of ChatGPT or not. We might not have. Do we do the iterating for? No, we didn't for the priority queue because you have to destroy it. So we didn't have that. So if you want to use each position or go through each position at a time, right, you use this cool yield keyword to say, hey, I'll give you something back, but I'm going to remember where I am so I can come back later when you ask for the next one. We can use that tree traversal that says, let's do left, center, right, and yield given positions as we go or values as we go. I don't know if we're going to gain a lot keeping position in here, but it's not going to hurt anything to be a position, I think. That's okay. All right, so we can come back to adding that in here. So to go and add a value then, we'll just define add, given an element to add. So if self.root is none, then we just add root, given the element. Right, that was easy. If it's not none, then, okay, well now we have to figure out, are we less than or are we greater than? Are we going to go left or right? So if the element is less than self dot root. Here actually, so let's see. So if we're less than self root dot, and this is a position, right? When we get root, let me go find our root here. Root is a position. So position will have the element function to return the private element. So it gets a little fun. So self root element here, right? So get the root, get the element from the root because it's a position. If we're less than that, then we need to see if it has a left child. So from the root position, left child, self dot left child of self dot root is none. Then we'll add left from self dot root and the element. Right? If it's not none, right, our else case here then, well then we need to recurse. Well, how do we recurse? We haven't told it where to start yet, so we probably want to have a helper function, right, that takes the element, or I'm sorry, that takes a position. So let's define a helper add here. Define add the element and the position. So you could tell me where we're starting here, and this one we can recurse. So we can call self add here, self dot add. Here's the element, and then the position is self dot root. Self dot left of self dot root. Right, find the left child because the left is not none at this point. And really, all of this code is going to be the same here. This is a little bit ugly here, so it might be nice to say, hey, we can default this to none. And if my position is none, then we can say position is equal to self.root. And I think we've seen this kind of format before. We'll say, hey, if you don't give me anything, I'll assume it's the top. And I think we did that with, was it height? One of these ones? We did, yeah, the height. If you don't give me the position, I'll assume you want the height of the whole tree starting at root, right? And then use this private helper function that takes a position. So same idea here with our add. So if you don't give me a position, we'll assume it's root. Then I can use all the same logic here, and life works out pretty well. So if the root is none, we add a root, we're done. Otherwise, we'll call self.add the element from self.root. Actually, we don't even need that because it will default to root then, right? Is that the element? That's not going to work, is it? No, sorry. This is private. Yeah, this is private. We can give it self.root. Or we can give it none. I keep going back and forth. I'm sorry. We'll just do the private add to this. So if the position is none, we have root. And then instead of root here, this will just be my position dot element. So you gave me the position, get the element out of that position. Great. If we're less than, see if we have a left. So position is the thing we're going to check the left child of. If it doesn't have a left, we'll add a left of the position. Right? Add left given the position of the element. If it's not, then we'll call our private helper function, adding the element from the left of the position. You with me so far? So this should just keep going left and left and left and left and left until it no longer has a left child. We become the left child because we're less than. If we're not less than, right? Well, okay. So if we're not less than, we must be equal or greater than. I guess we should check first. So we can say, hey, if the element is equal to position dot element, and raise a value error or something and say, hey, duplicate value. Because this idea we have to be a set. Because if you're equals, you can't be the left or right, and we're not in the form of a binary search tree. That's no good for us. So for less than, we do this. If we're not less than, you got to be greater than. Right? So this is just our else case here. we're going to check, hey, if my self.right of the position is none, then great, we can add right. Self.add right, given the position and the element. If we didn't do that, then we need to recurse on the right. So we'll call add given the right of the position, because we're greater than current position. Right? Less than current position, greater than current position. So does it make sense? We can use this recursive form and just say, okay, keep on going until you're less than or greater than, and there is no child in that position. So if we add things in order, we had a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we'll get that ugly chain of 1 is a root, 2 is a right, 3 is a right, 4 is a right, which is no good. And we need to do some balancing later. And that's the thing you can look at later on with the AVL trees, red-black trees, is how do we rebalance ourselves so that we are more of a full form. Now, you're not guaranteed to always be full. The idea that every level has all the children the entire way, or a complete tree, a full tree, that's okay. We just want to be close to that because it'll give us better performance. If we're close, then we can assume we'll get that logarithmic performance because height is logarithmically based of size n. And that's the goal here. So adding then should, on average, right, on average, be O of n, or log n. Right? The height, or what levels, is log of n. Number of levels, is that fair to say? The number of levels or the height is log n. So should be. The worst case, though, right, case is O of n. We need to do balancing. Prevent this. So if you are a balanced tree, mostly balanced tree, you can take care of this. Again, we're not worrying about that right now. That's an exercise for later. Okay, so that works out pretty well. So to get a particular value out, right? This idea of do I contain a value? That is a common thing. You ask a list, hey, is this in your list? Right? We can add that function in. Is it the not index? Contains? Yeah. If we contain an item. I don't know if we've done this one before, but to say, do I have this value in here? Same idea. This is recursive structure. If we're less than this position, go left. If we're more than the position, go right. So here's our initial contains then. Now, you don't need recursion, right? Recursion makes things easier for us, but this is essentially kind of a loop, right? So we can say my current position, we'll just say position, right? Position self root is the first position. So we can say while my position is not none, let's keep on going. Because if we get to a none position, we haven't found the item. Is that fair to say? So if it's not none, we can keep on going. So if the position dot element is equal to the item, return true. Right? If it's not, then what do we do? Okay, well, I need to see if it's less than. So if my position, if the item is less than the position dot element, we need to recurse. We don't even need to recurse though, because this is a while loop, right? We could recurse, or we could just say, okay, let's change position then. So position will equal self.left of the position. Go to the left child because you're less than. The loop keeps on going then, right? Comes on back. Is the position not none? Okay, let's check. Did we find it? If not, are you less than or greater than? So if we're equal to is one thing. Otherwise, same idea. Else if here, if else. If we're not less than and we're not equal to, you've got to be greater than. We'll say my position is equal to the self.right of the position. Is reassign position to the right child. Move to the right. If it's not none, check if we matched. Right? If this loop stops, arrays a value error, and I don't know, say like item not found or something, or what, item not found, right? We didn't find it. It wasn't in here because otherwise we would have returned a true. Or I guess we just return. Do we just return false at that point? I guess that's just return false. Sorry, we just return false. Because if we didn't return a true, and we got to a none position, it's not here. Right? If we look back at this tree, hey, if you wanted to find, I don't know, say the number 13, we say, okay, does 15 equal 13? No. Is it less than? Yes, go left. Does 12 equal 13? No. Is it less than? No, go right. Does 14 equal 13? No. Is it less than? Yes, go left. Oh, position's now none, return false. We do not contain a 13. So again, the same performance for this then is on average should be log of n. Could be terrible if we don't balance this tree out. So I know we keep waving that. Like we'll solve it later, but really you will. Okay, we'll just acknowledge it can be bad. We can go from there. So the same sort of add recursive. You don't even really need to do this with a recursive method either, right? This could be a loop, just like you did with the contains, right? We could just say while. We got lots of options. This one's a little trickier because it's like while the left child is not none, or if the left child is not none, and so I like the recursive call here. A more efficient tree wouldn't have this is all. But again, either is okay. It gets the job done for us here. All right. So I did promise we'd come back to deleting an item. This gets tricky. If we only have one child, then it's not too bad. We can just put that child in our place. It fits. If we have no children, that's easy too. If we have two children, so say we wanted to delete the 12 here. Oh, sorry. So if we wanted to delete 23, it has one child. That's really easy. We just put 18 in his place. If 18 had a left and right, perfectly fine. They can just stay there. Nothing has to change with the left and rights here because we only had one child. If we want to delete 18 that has no children, really easy. We just delete it. No biggie here. But deleting 12 is tricky because we have two children. We have the 7 and we have the 14. Now, we could put the 14 in because it has no children. That's easy. If 14 had a left child, it couldn't go in because we already have a left child here, right? We can't just simply swap our values out, right? If it had a right child, we could put it in. So there's a lot of like funny edge cases you can get to for this that are going to cause trouble for us. Or, hey, if we wanted to swap the 7, sure, that works because it only has a left child. If 7 had a right child, say we had like a 9 in here, we couldn't do that, right? Because it has two children. We can't just take that value. So what we need to do is come up with, well, what are we going to swap then? And you got two options. To maintain our form, you can either take the smallest value on the right side here, or you can take the largest value on the left side, because that will maintain the form. So the largest value on the right, the largest value on the left should be larger than all the other values on the left, right? The smallest value on the right should be smaller than all the values on the right, all the other values on the right. So eventually, you can find that smallest child here. So I'm going to erase these two circles here. So you can either go left and then go all the way right. So go to your immediate left child and then go right, as far right as you can, because that will be the largest item. Once you reach something that has no right children, we're done. Right? So 9 is fine. If we had more values in here, if we had a 10 in here, that's fine. If we had an 11 in here, that's fine. Right? No biggie here. We find the largest value on the left, and we're going to just swap the value in up here. So we'll get rid of the 12, we'll put in the 11, and we can erase the 11 here. That one's done. Right? Now, because this is the farthest right, it can't have two children. Right? Because if it had two children, there'd be another right for us to go. So that's an easy swap. Even if it has a left child, it's an easy swap. We just swap it in. Right? It might have no children, it might have a left child, but it can't have a right child. So it can't have the same problem where we don't know what to put in here. So it gets a little messy. But to delete then, right? Delete a position. Sure, if we're going to use position, we already have that. That's okay. We're going to skip this. So if the number of children is 2, this is the hard thing to do. So we're going to swap with, now do you want to go to the largest left child or the smallest right child? Either should work. Okay, the largest left. Largest left. Our largest item in the left subtree. That the subtree, the tree root of that, my left child, we got all sorts of terminology when it comes to trees. Okay. So we need to go find what that is. So we're going to have the position then will equal self dot left of the position. Right? And we know we have 2. So we're good. So that we'll at least have this position because we have 2 children. Now, if this has no right children, that's it, we're done. It's okay, but we're going to keep on going as long as this one has a right child. So we can say while my self dot right of the position is not none. If it has a right, let's keep on going. We'll say position then equals self dot right of the position. Right? If there's a right child, move the position, walk the position to the next link, walk the position to the next link, walk the position to the next link. Go find that next right child, the next right child, the next right child, the next right child. When we're done, we know this position has no right child. Right? That's it. That works out pretty well. So then we can swap now. If we have a left child, we can swap. So if the self.left of the position is not none. So if it has a left child, right, it can't have a right child, then we need to swap. So to swap that, then I don't think we have a given swap currently, right? We have a add contains, yeah, we don't have that. So we need to see. So we have the position, we need the node out from underneath because the node is the one that has the links, right? So we're going to validate the position, which will give me back the node. And we haven't done this validate in a while. So if it has a left, then we'll take the node is self.validate given the position. Okay, so now we've got the node. The node has the link to the parent. The node has the link to the left child. So I can say node.parent, node.parent dot right child. The parent, no, yeah, it has a right, right? The type ahead wasn't working for me. That's okay, because this is another node. Right, yep, okay, right. Parent dot right will equal the node dot left. Right? My left child now becomes my parent's right child. Right, so this, if we had, let's change this here. Let's say we had 9. Let's do it with 14. I think we have a little more room here. So if we 14, if we had like a 13 here. So if we want to delete this node, right, we're going to go right far possible. We'll get to 14. 14 has a left child. So 13 will become the right child of 11. It's larger because it's on the right and it fits. If it has any children, great. We don't have to change a thing here. The number of children doesn't change because it could have left or rights. It could have none. It could have one or the other. We don't care because we're the furthest right. Right? If it's on our left, it's got to be less than us. So we don't need to worry about that. So we'll just do a swap. Now, after I've swapped that, now I can say node.left.parent is equal to my node.parent. Right? So say, hey, parent, here's your new right child. It's my left child. Hey, left child, your new parent is not me. It's now my parent. Right? We've done the swaps to put it back in the chain here. Again, if we're using the index-based storage, this works out a lot easier. You don't have to worry about any of these links. So the links are a little tricky here. If we had that linked or the array-based storage, you just change its index, change its position, we're done. Works out a little cleaner here. So this is a little bit weird, but it's okay. So if self-left is none, there's nothing for us to do, right? Except for tell my parent that I no longer exist. So we'll validate here, and then we'll take my node parent's position and its right child and set it to none, right? Because we're done. Take ourselves out of the chain. all of this now to swap. So the node here is what we're going to swap with the node up here. So we should probably rename this here. This is the wording's a little funny here. So this, maybe we shouldn't even use position. I think I want to keep. So the original node will have the element, right? The node has the element. So all we need to do is change the element there from this node. So we don't want to rename node because we need to reference this one here. So this will be, or maybe we just call this one the original node. That we never use node anywhere else, right? We'll call this the original. The original node. Okay. After we've done all of that, then, so node will have a value, right? We had a left, we swap. Okay. So either way here, then, the original node dot element can equal the node dot element. We'll take the value from where we found, right? This is the last position, the furthest right position on our left. Right? We kept on walking right, kept on going. We can take that node's value and stick it in the original node's value. Right? We probably even want to, no, we don't even need to delete. I guess we can save the old value. So old value is my original node dot element. Change the element, and then we can return the old value. It's probably proper, right? When you delete something, we'll just give it back because we're deleting by position instead of by value, which is a little weird, but that's okay. Oh, here's the node here. Oops. So that's why we had node. Should we just change this one here? Put this back. Or we can just say node equals the original node. There we go. That's easier. So instead of renaming a bunch of stuff, this feels bad. But that's okay. It should do the thing that we need here. Okay. Eventually reduce our size by 1. Life is good. So if all of this happens, then, right, all of this then is the else case. Right? If we have 2 children, do the 2-child thing. Otherwise, do the 1-child thing. Life is easy, right? If we have a child, swap. No worries here. You can just throw that child in. Set. If we only have 1 child, right, then it doesn't matter if it has 2 children or not, 1 child or not. It just goes in our place. Life is good. How you feeling? This is a little nuts. A little crazy. But it's ensuring we stay in this binary search tree form where everything on the left is greater than, everything on the left is less than, everything on the right is greater than. Now, just as a fun exercise, maybe, there's a common interview question that says, hey, I'm going to give you a binary tree, like 7, and then 5, and 12, and 6, and 15, and 6. Let's do this. Let's make this one like 3. Sorry, let's do like 3, and 5, and 1. So if I give you a binary tree like this, how would you go about telling me if it's a binary search tree or in the form of a binary search tree? Just kind of as a thought exercise. And it's a common interview question because we seem to like to ask people if they know data structures. I think the idea there is that if you're able to talk well about data structures, people feel like you understood some of the coding stuff that you learned. And if you just barely squeaked by, maybe some of the other stuff didn't stick as well in education. I don't know. It's not the best interview question, but it's relatively common to ask people about data structures because we're just a weird industry. So what could we do? Okay, so let's check this node. Is the thing on the left less than 7? Is its left child less than? Yes. Is the right child greater than? Yes. Okay, what node should we check next? So this one's check. What's next? Okay, so 3. Is its left child less than? Is its right child greater than? Great, check. 1 has no children, check. 5 has no children, check. 12. Is its left child less than and its right child greater than? Yes, check. Has no children, has no children. Is this in the form of a binary search tree? No. There's a 6 over here on the right of the 7. You can't have anything bigger than you on your right. It's not a binary search tree. So BST, not a binary search tree. Every node individually checks out, yes. Each node has directly its child less than and greater than. Doesn't mean we're a binary search tree though. So what's another way we could go about seeing if we're a binary search tree or not? We can't just look at one node at a time. Remember we talked a little bit about iterating and the idea we can go in this in order traversal. I can go left, center, right, left, center, right, left, center, right. Well, one approach is to do that and see what you get out. Right? So if we were to follow the left, center, right, okay, so we call iterate. Do we have a left? Yes. Okay, we go here. Do we have a left? Yes, we go here. Right? We get a 1. It has no left. We do the center. It has no right. That call's done. We come back to here. We did the left. Now we do the center. We go to the right. Left, center, right. There is no left. We do the center. There is no right. We're done. This one's done. We come back to the 7. We did the left. Now we do the center. Now we do right. We go right, left, center, right. It has a left. All right. Does this have a left? No. We do the center. Okay. We do the right. Nothing in the right. We come back. Do 12. Now we go to the right. It has no children. We get 15. Is this in sorted order? No, right? Because the 6 comes after the 7. So as we're traversing the tree, if you get to an element that's smaller than the previous element, you're not a binary search tree. So we can write a traversal, right? This idea that we can iterate over. So we want to define, what is it, iter of self? I think that sounds right. We had to steal that one, right? From the other book, probably has one for us too. Let's see. Let's just go ask ChatGPT. It can probably do it here. Let's see. I gotta log in. Yes, log in. Log in. Come on. I, I did. I think it's confused. Uh-oh. Come on. There it goes. Okay, sure. Why not? So given a linked binary search tree, structure like, let's see if we can give it some code and see what it does with it, right? Write an iterator function. See if it can read our code and understand it and give us something back. I haven't tried that before. I hear it's supposed to work. We'll find out. Oh, we had to think real hard. Look at that. It picked up the classes. An in-order traversal approach. That ChatGPT is smart. I don't want an iterator class. Oh, goodness. They're not as fast as I wrote code, right? It's slightly faster than I am. I can't keep up with the machine. I'm gonna be in trouble. So it's using a stack here and adding every node along the path of left, 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 left. And eventually, when we get to it, right, we'll take what's on the stack here, and then we'll add the path of what's on the right. And then we'll return ourselves. So we're going to get as far left as possible here, return that. When that comes off the stack, right, then we can go down the right path. So that works here. Not fond of this one though. I think the recursive solution is probably easier to follow. This one is a little funky. See if we can do this here. Neat. It has a recursive function. We'll challenge the bot here, see what it can do. And this is faster. It didn't change it, did it? It's the same thing. Oh, I guess I didn't use the stack. Okay. I don't think this works then, right? There's no... Yeah, that's not... It gave us bad code. We broke the bot. Right? This add leftmost doesn't do anything. It returns nothing and then it's not doing it right. Can we tell that that doesn't work? That's okay. All right, so we'll see if we can figure this out ourselves then. So to do our iterator, right, you can be our own iterator here. So we're just going to return itself. And then you have to define this next function here. So what is the next item here? Right. So when you're looping through, we need to ask for next. So probably need to track something in here, like where our current value is. Right. So we'll take our self dot. How about current node? I don't know, iterator position. And where do we want to start that? Let's start it at root. So self dot root. So when you ask for the next, then you say, hey, if my self dot current iterator position is not none, then we're going to go left, center, right. So starting with the root, right? If we're not none, then we can give it back something. If we are none, we're done. Right? This current iterator position is going to be done. There's nothing left to give, and that should be okay. So we need to go from root all the way left. Right? So we can say, how about a current position? Position is self.root. Oh, I'm sorry, is the current iterator position. I guess if left, right, we can do that. So if or while self.left of the self.current iterator position is not none, we'll take our current iterator position and keep going left. Self.left of that. That gets us as far left as possible. When that's done, right, we can yield the self.current iterator position dot element. Right, give them the element. When this code comes back, then, right, we need to now give them our parent. So we can yield the self.parent of this position. This gets messy, so we need to move the position right up to the parent. So self.current iterator position. I guess this should be while, right? All of this is a while here, as long as that's not yet none here. So this can equal my self.current iterator position, or no, self.parent of this. Okay, so once we've gone as far left as possible and given that back, now we move back to our parent. And we can yield the parent position, yield self.current iterator position dot element. So this is the left, this is the center. And then while that's done, we're going to go right and then as far left as possible. And go right. Now this isn't going to work. Shoot. All right, let's go to the book. The book has it. I was trying to do it off the top of my head. I'm sorry. Even the bot didn't help. 3. It's got an iterator in here. Search trees. Here we go. Okay, so it uses the after. That's what I was missing here. So to say the first position or last position of the tree, we go all the way left or we go all the way right. That's first and last. You could go before a position or after position. So if we have a right, then there must be something that comes after us. If we don't have a right, then go up to our parent and then see if our parent has something. That make sense? To see what node would come next. So it's, let's go back. We had our tree on this page, right? So there's 15, 11, 14, 13, 7, 5, 9, 18, 20. So this node here. So if we go to the first node, that's all the way left, the first node is going to be 5. What comes after 5? Well, if it has a child, we got to go to the child first. If it doesn't have a child, it's its parent. Its parent comes after because it was a left child here. 7 comes after. And what comes after 7? Well, we know we already did the left children, so we got to go to the right. What comes next? We go to the right child. That's 9. What comes after 9? 9 doesn't have it, so we have to go to its parent, right? But our parent was we were the right of the parent, so the parent doesn't come after us. The parent comes after us if we were a left of the parent. So we got to go to the parent's parent, right? If the parent was a left. It's a little messy. Let's do this. So let's add these in here. So this will be better. Get rid of these. So we'll add a first here. So then our current position is self.root. And while my self.left of the current position is not none, we're going to take current position equals self.left of that current position and just keep on going. I guess if the root is none, we're in trouble too, because there is no first. So if I don't know, is empty, create the value error or something. Empty 3. All right, sure. So we're empty. So first is all the way left. Okay, and then we can have an after a given position. So what comes after position is going to be this code here. Let's see if this copies in here. Oh goodness, that does not copy in nice at all. Ugh. That's gross. That's all right. So if right is not none, then we need to go right and as far left as possible. Right, so if self.right of the position is not none, then we're going to start at the right. So we'll have our, I don't know, current position will equal self.right of the position. So that's the immediate right. Then we need to see if there's anything left of that. As long as it has a left, go left, 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 right? Because it's on our right and it's the farthest left. That's the next smallest value. So while self.left of the current position is not none, our current position can equal self.left of the current position. Right? Eventually we'll get to the furthest left here, right? Then we can return that. If we don't have a right, okay, then our ancestor, right? We need to see if our ancestor is here. So this is our parent, right? So this is our current position. I guess we can call it parent, right? So okay, he uses ancestor, we use ancestor. Ancestor is self.parent of the position. So our ancestor, and ancestor is probably a good word for it here because the 11 is an ancestor, but it's not going to be the previous value. So you might have to go up another level, up another level, up another level to find the correct next ancestor. Does that make sense? Okay, so I think ancestor is probably a good term for it. So start at the parent, and then as long as it's not none, and we are the right of our ancestor. Because if we're a right, we're bigger than, or the ancestor doesn't come before us, right? So then we're going to say, what's this, while my ancestor is not none, and the ancestor is equal to the self.right of the, no, although the current position, there we go, so we need the current position. Current position, I don't like his term walk there, but that's okay, is the position. So the current position is the right child of the ancestor. Right? So if we're the right child here, and we have a parent. So if we have a parent and we're the right child, we need to keep on going. So up the chain. So our current position, I'm sorry, our ancestor is going to equal self.parent of the ancestor. So go to the next level up. Then our current position will also change because we need to see, hey, is that ancestor the right child of that ancestor? Because in this case, 11 is not the right child of 15, right? So if we got to 14, 11 is the parent, the ancestor. We're a right child though, so we need to keep on going. So then we go, hey, 15 was not, I'm sorry, 11 was not the right child of 15. So 15 will be the correct next position after 14. Because we found someone that's no longer a right child. So if we were 7, right, our ancestor is 11, we're the right child of that. I'm sorry, 9. So 9 is the right child of 7. 7 is the right child of 11. Right, so the next position then is not this one. So the next position, no, I'm sorry, no, 11. I don't know my rights and lefts. I'm sorry. 7 is the left child of 11, so 11 is next. If we're on the right-hand side here, so 18 is the left child of 23. So the next one will be 23. If we had a right child here, it's like 25. Our ancestor is 23. We're the right child of 23. 23's ancestor is 15, but 23 is the right child of 15. So it's not that one either. So it's at some point this needs to end where that ancestor is none. So the current position then becomes our ancestor. When that's all done, right, we can return ancestor, which might be none, right? If it is none, this loop stops, and we'll give back the ancestor. It might be none, it might not be none, right? Depending on what this case was here. So we should have, where's the iterator then? That's fine. Okay, so we'll add find iterator, iter of self. No, just iter. So self dot current iterator position is self dot first. And while my self dot current iterator position is not none, we can yield self dot current iterator position dot element. When that's done, we'll call self dot current iterator position is equal to self dot after the current iterator position. Go find the next thing, go find the next thing, go find the next thing, go find the next thing. And we yield as we go. So I think that would let us use this. Let's give it a try. Let's see, but we haven't actually tried any of this code yet, right? So that's a little scary. It might blow up in our face. So we'll make a tree, right? So here's our binary search tree, is a linked binary search tree. We should be able to call add. Let's go add our values. We had a 15. Add, and then what do we have here? We had an 11 and a 23. And then how about a 7 and a 7? So if I do them in this level by level, we should get back this form, right? Was my idea to make this easy to add these and get this form out. So then a 14, 14, and then we had an 18 and a 25, 18 and 25, and then we added in a 5 and a 9 and a 13, 5, 9, and 13. I can say for value in my BST and print the value. So if the iterator works for us, this should print here. And I think, what did they have? They had the none, right? It kept yielding a stop iteration. So if it's none, we'll stop iteration. That's probably important here. Let's check that out. So when it is none, then we can raise the stop iteration. Probably we'll just stop the iteration cleanly. I don't actually recall. Let's give it a try. Oh goodness. Iterator return non-iterator of type none type. Uh-oh. Iter. Oh, we need to return self. That's right. So we set the first position. Uh-oh. Looks like we had an infinite loop here. Those are all, oh, those are different values. B0, 40, B0, 40, B0, 40. We can say if I self.current iterator position is none, self.current iterator equal to self.first. Something in here I think we need, because I think I was resetting it wrong. Nope, that's bad too. Oh goodness. That's still failing on us. Okay. Let's see, I guess we should pause and see what happens when we add here, right? See when we get to like adding a 7 maybe? Run the debug mode. Okay, so we get to here. So our binary search tree has a position, right? It has the root here. So the root should be 15. 15 should have a left. Left should be 11. Okay, that's good. And then right should be 23. right to 23. Good so far. So then when we step through, then the 11 should have a new left. Should be the 7. Okay, good so far. And then the 11 should have a right. Left. Yeah, the right here is 14. Good so far. 18, 25. These are probably adding in okay. So let's step into our code here. We're going to return self. It's not doing the next code. All right, we need to go steal the right one from the book then. Where's our iterator? After find position, get, find, get and set, iterator. Oh, here it is. Okay. Oh, all right. We don't even need to do the next one, I guess. That's cool. I did a bunch of extra work that we needed then. Does this just, yeah, yields the value? Okay, sure. So self dot current iterator position is self dot first. Well, it's not none. Yield. Keep on moving. We're done. It doesn't even raise an error. Okay, sure. Let's give that a try. Nope. Did I get any values back out? Uh-oh. So is first not working then? First. Oh, we never returned it. Oops. Return current position. That'd be useful, right? If we actually return that current position for first. Oops. Oh, okay. All right. Then we're stuck in a loop. So we get 18, 23, 25, 15, 18, 23, 25, 15, 18, 23, 25. Something's not working right. Let's see. So is it our after then? Let's see. Probably our after code. Let's take a look at after. So we got 18, 23, 15, 18, 23, 25. Do we get the original values out? Yeah, 5, 7, 9, 13, 14, 15, 18, 23. So it didn't end after 25. So it should have ended at 25. And something wasn't ending here. So we get the ancestor is the parent of our ancestor. Current position becomes the, oh, this is wrong here. We did this in the wrong order. So we said, hey, the ancestor became the parent, and then the current became that new ancestor. We swapped them in badly, right? Because I was trying to change two values, but I ended up changing current to this new one, so they're the same value here. This ancestor is the same as current position. That's our problem. So current position needs to move to the ancestor first. Then the ancestor can become its own parent. Let's see if that works for us. Hey, look at that. I'm kind of amazed it worked. And it's only 3:09. We had like 6 minutes to spare. All right. How do you feel? This was a little nuts. But basic rule, everything smaller on the left, everything bigger on the right. We'll get to balancing stuff in another class. We don't need to worry too much about that. And going through it then, finding the next value is a little tricky. This whole process of what comes after me is a little awkward, right? Because depending on where I am, if I have parents, if I have rights, if I have lefts, but it's this recursive nature. And we're just using loops here, right, instead of recursion. But it's the same idea. Just go as far left as possible here. To find the next thing, you have to go right if you have a right, and then go far left as possible. If you don't, you have to go up to the parent, right, and see what happens. All right, cool. So we took this one out of the book, right? This was book page 462. should be good about citing these sources here, right? After, oh no, that was after, right? That was 462. Page 462. I forget what page was the iterator on. That was further down, right? That was this one. Is that 472? There you go, 472. All right. Questions, thoughts, concerns? How's it going on the project? Yeah. Okay. You stuck on anything? Any pointers, or just haven't started yet because it's not due for a while? That's fair. That's fine. We've got some time, right? That is due 28th, next Tuesday. Yep. So we're mostly done with the stuff we want to cover. I don't know why I keep saying we. It's me, right? The things we want to cover. The AVL trees, splay trees, 2,4 trees are back. Those are all advanced topics here. Just our binary search trees in general. So I think we're okay to move on a little bit here. We had more topics here of sorting and selection we can get into. And then on the 28th, we'll get into the project solution and talk about the final project. And then the 30th, we'll pick up whatever sorting and selection we need to. Does that sound okay? All right, awesome. Let's plan to do that. We've done a little bit of sorting and selection already, so we'll look a little deeper in here. We don't get super deep either. We start with the basic ones, and we'll go from there, okay? That way we can do the final project starting the 28th, and then we'll have time these other weeks here. It won't take the whole time, I think, for these. Ethics is fun, and then we'll have time for that. We'll have an ethics lab. The last lab we'll have time for as well for final project work time. All right. Awesome. Folks, take care. I will see you on Thursday then.